All right, back to gravitation. The gravitational force between two masses is gm1, m2 over the distance square, and that's the main idea. Looking at the Earth and an object on the Earth, if the object is small m, and if the Earth's mass is capital M, so I'm now using not m1, m2, I'm just using small m and capital M. Obviously, capital M suitable for this and small m for me. And the distance between me and the Earth right now is just the radius. It's just the radius of the Earth. So now, using this equation, what is the force that is acting on me? What's the force that is actually acting on me? It is G m over r squared. Is that okay? And it is that force which we denote by the weight. So the force of gravity, the force of gravity is the weight. The force of gravity, according to the Newton's law of gravitation, is simply the weight, mg. So look at this equation now. M and M cancels off. So what you have now is G is equal to Gm over r squared. So if you want to really find the acceleration due to gravity on the surface of the Earth, just plug it in. Plug all those numbers in, because we know capital G is 6.67 10 power minus 11. Capital M is 6 followed by 24 zeros. And radius of the Earth is 6.4 times 10 power 6 meters. And then square it. So you'll end up getting 9 point whatever. Okay? So that is the acceleration due to gravity on the surface of the Earth. Now if you go to a different height here, if I'm taken to a different height, let's follow the same thing. I definitely weigh less over there because I'm going further away from the Earth. Now how will this equation be changed? For this location, how is that equation going to be different? That equation is going to be force of gravity is equal to the weight. But what's the force of gravity there? Is Gm over r plus h squared, because I'm going higher now. And on this side, the weight, I can't write it as mg, because do I weigh this? Say that again.
The acceleration due to gravity
Is different, so you write mg prime. It's a new g there. So when you go to a different height, you're talking about a different g. Definitely not 9.8, it will be lower. So we are in a region where the acceleration due to gravity is weaker. And so that is g prime. Do the same thing again. You see that g prime is gm over r plus h squared. And this equation actually will give you something very, very important. Look at that. If you cross multiply, you get this. Now this equation is an important equation. Why it's so important is because it connects the capital G with the small g. Not just for the Earth, but universally. You can apply that for any planet. You can apply that for any mass. You can apply that for any mass. So if I have a baseball of mass m, if I have a baseball of mass m and of certain radius, what is the acceleration due to gravity on the surface of the baseball due to the baseball? Not by the Earth, by the baseball. All you do is just plug in all those numbers, you get the g. It will be very weak, right? Because mass is small, So it is going to be very weak, but it is definitely there. So every object has its own acceleration due to gravity to itself, but it's pretty weak. Now, so therefore, like buildings, yeah, they have an attraction. You're getting attracted to it, but it's not significant. The biggest attraction is by the biggest object right under you, and that is why when you're released, when you jump off, you don't get stuck to a building. You fall straight down because that force is negligible compared to the force with which the earth is pulling us down. You understand? It is no comparison at all. That's why everything kind of comes downward, not mutually going sideways. Now, if you're talking about a bigger, very big, like moon is big enough, very big enough, and so it has a bigger gravity than any other object. Earth, of course, has got much bigger because Earth is heavier and bigger. So Earth being heavier, it is definitely having a larger gravity because it's heavier, larger gravity. The moon is actually smaller. That means the radius is actually smaller, but the mass is also considerably small. And that's why the gravity on the moon's surface is like 1/6 of that of the Earth, approximately. So every planet, every star, every object in the universe will have a certain acceleration due to gravity. You understand? And that changes according to the height, like this. So if h is equal to r, what will be the g prime? If h is equal to r, that means you're gone exactly one radius higher. If you go exactly one radius higher, put h is equal to r, what will happen to the denominator? It will be 2r. So 2r the whole square is 4r square. So what happens? It will be gm over 4r square. Now remember, gm is gr square. So if I plug this in here, if I take that and put it right over here, we can write on one more step. So g prime, if I just plug that straight over here, I get gr square over r plus h square. So what will happen if h is equal to r? It will be g prime is equal to gr square over 4r square. R square is gone. So the g prime is equal to g over 4. This is when you go to a height which is equal to 1 radius. Now you can see what happens if h is 2r. If h is 2r, what is g prime? If h is 2r, the entire distance becomes now 3r, so 9. So g over 9. And if h is equal to 3r, then the g over 16. Make sense? And if I plot this on a graph, height from surface. The height from the surface. Initially it is g. And when you go 1 radius away, it becomes g over 4. When you go 2 radius away, it becomes g over 9. When you go 3 radius away, it will be g over 16. 4 radius away, it will be g over 25. And it goes down exponentially that way. So by the time you go a good amount of distance, it drops down pretty small. So what if you go 9 radiuses away? If you go 9 radius away, It'll be, yeah, these are things you can do by just imagining all those numbers going in there. G over 100. Because 9 radians away, in terms of height, 9r plus 1r is 10r. 10r, so basically it's going to be 100 times smaller than your 9.8, which is how much? 0.098. You get it? 0.098. It's almost like 0.1. Almost like 0.1. That is how, like, just 9 times the radius of the Earth, which is 9 times 4,000 miles. So 36,000 miles up. 36,000 miles up. The G there is like 0.1 meters per second square. You get it? So G goes drastically that way. Now, what if you go into the Earth? Into the Earth. The story is entirely different. Into the Earth, the story is totally different. Look, into the Earth means like you're going deeper. So let's go that way. So when you're that deep, when you're that deep, you are literally standing on a smaller Earth. Because what is under you is a smaller Earth. Not all the mass is above, under you, right? Do you understand that? So it's like you're standing on this Earth. You're standing on a smaller Earth. And this part of the Earth acts as an atmosphere for you. Like, you understand what I'm trying to give you? So that's the Earth. Right now, the entire Earth is under you. The entire Earth is under you. All the mass of the Earth is right under your feet. And the air, the mass of the air and all those things, we don't even care. Why? Because it is above us. It's around us. Now, will the air also impact some gravity on you? Yeah, they'll also be pulling you. But the pull by this atmosphere is going to cancel off. Because if you look at it, you're standing here. This is the mass of the Earth you're standing on, the new Earth. And this part of it is going to behave as atmosphere. All this matter that is around above you, this whole thing is going to be the atmosphere for you. But not made up of air, but made up of, Earth. So this section of the matter is going to pull you down, and this section of the matter is going to pull you that way. You're here. And although it's only less material above you and more material below you, this more material is further away from you. You understand? And so the forces offered by all this on you is 0. The net force is 0. This can be actually proved using calculus. The net force of all this matter on any object inside is supposed to be 0. So this object will be influenced by only the mass which is inside. Anyway, we're not going too far into it. That's not the scope of this particular topic. Here we are more interested in the circular motion concept, right? But I'm just letting you know that the deeper you go, you're standing on a smaller Earth. So the equation is going to be mg prime is equal to g. I'm not going to put capital M, but I'm going to put capital M prime. It's a new Earth. Over r minus d squared. Because, r minus d. You're on the smaller Earth. So the radius of the smaller Earth is r minus how deep you went. Now, if you keep going like that, M prime is going to drop. And that is going to be changing as well. But ultimately, when you go right to the center, you're not sitting on any mass. The mass, the capital M part of it becomes 0, which means you are standing right in the middle, and all the Earth is going to act as an atmosphere for you. And the pull by all the matter is going to be even, and the net force is going to be 0. So what's the acceleration due to gravity right in the middle? 0. So acceleration to gravity is 0 right here. And as you go higher and higher, the acceleration to gravity is going to change. And in fact, we can prove it that the change is linear. So if you go into the Earth, if I go into the Earth exactly 1 radius inwards, inside. If I go 1 radius into the Earth, which is basically going to center, right? If I go exactly 1 radius into the Earth, the acceleration due to gravity drops down to 0. It's linear, pretty much linear. It is linear if you assume that the entire density of the Earth is kind of uniform, but it's not true. The material here is more dense than the material around us. So it won't be perfectly linear, but assuming that the density is uniform, we can say it should be straight. So G is 9.81 here, and right in the center is 0. If you go halfway down, it'll be exactly half of 9.81. If you go 2,000 miles instead of 4,000 miles, it'll be like halfway, 4.9. Make sense? So it's a linear relationship. So if you go 4,000 miles deeper, G will drop from 9.81 to 0. If you go exactly halfway down, it'll be halfway. It is not exponentially going down, like outside. Inside is going to be straight line. Clear? So you know how the G is varying if you go out of the Earth and if you go into the Earth. Into the Earth is not very important for us right now at this point, but these are equations that we will use again and again. Now let's think about orbital motion. Orbital motion. Now things like the moon is in orbit around the Earth. The satellites are in orbits around the Earth. Okay. So if, yeah.
This is still a part of circular motion, it's its whole new chapter.
Which one?
Is it orbital motion? It's in a new chapter.
Oh no, this is circular motion. Yes, pretty much circular motion. So all I did just now in terms of gravitation was just to introduce you to gravitation, so we can get into the orbital motion. Now we are back into circular motion again. We are back into circular motion. All right, here is the Earth. The mass of the Earth is m. So what is this orbital motion? What do you mean by orbital motion? Things going round and round? How's something going round and round? What motion is that? Okay, let me get you through that one. Watch. If I take this marker and drop it, it falls straight down, right? Everyone knows it. Okay, now if I take the same marker and throw it sideways with a small velocity, what happened there? What kind of motion is that? Projectile motion. Now why did it go in that? Why did it take that trajectory? Gravity is pulling it down, but I gave it a velocity horizontally, and so it was scooting that way as it was falling. Correct? Now what if I throw it faster?
It's further.
It goes further. So now let me go to the picture. Let me go to this picture again. Let me say I'm standing on a tower. I'm standing on a tower, and I'm taking this marker and throwing it. If I throw the marker gently, it falls there, correct? If I throw it faster, it falls there. That's a lot of distance. If I throw it still faster, it falls there. It has to come down. So unlike here is landing straight there because the ground is horizontal. But if you look at it from a bigger scale, from bird's eye view or even from a star's view, then you're talking about the ground is not straight, flat. It's curving. And that's why it is delaying to land. If the ground was horizontal, it would have landed here. You understand? But since the ground itself is curving, it's landing further away. So if I throw it faster, it'll land here. And if I throw it still faster, it'll land here. And if I throw it just fast enough, it will keep falling, hit my head. It'll keep going round and round. Because it is falling. But it's never going to reach the earth. Because the earth is also curving the same way. Get it? So if I throw it at just the right speed, I will be getting this marker in orbit. So, is the marker falling? It is falling. But is it not able to reach the earth? Because it's falling at a rate that the earth is also curving. You get it? And that's the reason why it is continuously falling and it is moving in this kind of a pattern, which is what we call as orbital motion. If you look at it one way, it is projectile motion. It is projectile motion, but it is orbital now. Why it's called orbital? Because this cycle repeats. It's never going to land. So, is this marker going in circular motion? Yes? No?
Yes.
I told you it's falling. So, yes. Is it going in circular motion?
Yes.
That means some force has to be provided. The gravitational force is the one which provides the centripetal force. The gravitational force is the force that is actually providing the centripetal force for it to go round and round in a circular path. So let me say this, like the tower that I'm talking about is not too high. Let's find out how fast I should throw this marker in order to get it spinning round and round the earth. How fast should I throw this? Or how fast should you be driving a car to set yourself into orbital motion? Right? So if you drive your car and reach a certain speed, you can just turn the car off and you can just go round and round the earth. Keep going. That is orbital motion. But we have difficulties. If I'm going to try this, the marker thing, it will fail. You're not going to set it into orbital motion. Why?
I don't think you can throw that hard.
I have a question.
Yeah, question. Tell me the answer for this question.
I don't think you can throw it that far, Coach.
I can. Yes. Air resistance. Yeah, okay, yes, I can throw with that velocity, but what happens after that? This marker will just burn off because the air resistance is so high that anything going at that speed in this atmosphere will burn out, completely burn out. So no chance of it. So the only way you can set things in orbital motion is you have to go out of the atmosphere. And the atmosphere gets thinner and thinner as you go higher and higher. And by the time you go 100 miles, it's done. There's no atmosphere after 100 miles. So safely 150 miles, nothing is there to bother. So if I take the marker to 150 miles up, 150 is not too far away. Look, from here to here is 4,000 miles. Where is 150 miles? It's not too far, right? On a scale, 0 to 4,000, and then 150 more miles is nothing at all. How many miles from here to Cincinnati? Yeah, 90 something. Yeah. From here to, anyway, you know what 150 miles is approximately like, right? 150 miles approximately is, so think of going 150 miles upward. Just think of going 150 miles upward, not sideways on the Earth, and you will be able to cross the atmosphere. So all the orbital motion, all the satellites and all those things are put in at a height of about 150, 200 miles. Nothing is below, because you can't put it, because the atmosphere is there and it will mess it up. So let's find out this. If I am really trying to drive a car, how fast should I drive in order to be orbiting? In order to orbit, the two forces are this. The gravitational force is the only force that is acting on the object, correct? What is pulling us down is gravity. And that should provide the centripetal force, because there's nothing else. Assume no air resistance for the time being. Assume there's no air resistance. Gravitational force is equal to centripetal force. What's the equation for gravitational force? G m m over radius squared. So how fast should we drive on the surface in order to orbit? That's what we're trying to find out. So the forces that are acting are supposed to act. One is the gravitational force, which is supposed to be the force with which the Earth is pulling us down, and that should be the only force. We don't want the normal reaction. And so that force is supposed to provide the centripetal force for us to keep going. And what's the equation for centripetal force? Right? Isn't that the equation for centripetal force? Okay. Cancel the masses. What does that mean? Whatever be the car, that's fine. You can have a Land Cruiser or just a motorcycle, that's fine. It is independent of what is spinning. So satellites can be any mass. The most important condition is that, the speed. Look at that. One radius also cancels off because of the denominator. Yeah.
So what is independent from the mass?
Because the mass is gone, cancelled off.
Right, but what specifically?
Because the more the mass of the object, the more the gravitational pull, and that it's the more the centripetal force. So centripetal force and gravitational force both depend on mass. So if the mass is bigger, then both will increase accordingly. So that's why you can see that the mass is getting cancelled off. That means it is not dependent on the mass of the satellite. Yeah.
Instead of R, I'm just wondering, say you were higher up.
Oh, we will talk about higher up after.
Okay, so it's not just D.
But right now we're talking about a car.
Yeah.
And you're not anywhere, you're on the surface. So let's talk about a car now, and then we'll go from there to higher. Okay? So we're talking about if you have to throw something standing here, how fast should you throw so that it'll come back here? That's what we're trying to do. So these are cancelled off.
Okay.
And what is GM equal to? What is the product of G and M? GR squared. I just gave you that, and you have the boxed equation. For the Earth, it is GR squared. See this? I'm just replacing capital G times capital M with just GR squared. Now you can see that this R is also gone. So finally you have V squared is equal to GR. Will that help you to find the speed? Go ahead. So V is square root of GR. Substitute 9.81. You can actually use capital G and capital M as it is and go on also, I'm just showing you another way of doing it. So times R, what's R? Yeah, but we don't use miles. 6.4 times 10 power 6. No squaring here because it's just R. Tell me what answers. What do you get? The answer you get will be meters per second. Yeah.
7,919.60.
7,919. Yeah, almost 7,920. I'm rounding it up.
Brisk walk.
7,920 meters per second. That's the speed at which you're supposed to go. Which will be how many kilometers per second? It is 7.92 kilometers per second. Which is how many miles per second? What do you do? Divide by 1.6. What do you get there? 4.9 something? Divide that with 1.6.
4.95.
4.95 miles per second.
Do that on the way.
If I can drive at that speed, then I'll be in orbit. 4.95 miles per second. That means basically, what will be the distance from here to downtown? Maybe same. So you're going from here to downtown in just 1 second. Like, you're already there. You're already there. So that speed will be the orbital speed if you are just very close to the surface of the Earth. Yeah,
What is that in miles per hour?
that's what it is. Oh, miles per hour.
Per hour.
Just multiplied by 3,600. Because 3,600 seconds in an hour. So multiply 4.95 times 3,600.
Calm
That's
stroll.
3 seconds.
That will be miles per hour.
That's a lot.
All right. So if I have to throw this marker, all right, pay attention. If I had to throw the marker, I had to throw at that speed, 4.95 miles per second, in order to get it in orbit. Because if I throw at that speed, it is going forward. At the same time, it's falling. It's falling, and it's going forward. It's falling and going forward. And even though it is falling and going forward, it never reaches the Earth. You get it? It never. So satellites, once it's put in the right orbit, the right speed, and all that, it's supposed to keep going. You can turn off the engines and it will keep going. That is basically orbital motion. Now, the practical difficulty of something so close to the Earth's surface is because air resistance is a killer. It will reduce the speed and it will burn the object up. So no object is going to survive at that speed. That's why when some things enter from the outer, outside space, if something enters into our atmosphere, it burns off, unless it's really, really big. It just burns off because of friction. So it's just basically a fireball. You see, nothing will be remaining. Everything, metal, everything is going to burn and vaporize. So nothing is going to come back here if it is a small object. But if it's a big object, then no matter how much it burns, still the content will still remain, and then it comes down and hits. So that is the speed. Now let's find out what will happen if I go higher. So in order to escape the Earth's atmosphere, you need to go higher. So let's go to some height and then do the same thing again. Let's go to a higher altitude and then do the orbit. So we don't want to do it from here. Instead, we want to do it from a height which is just above the Earth's atmosphere. And I said atmosphere finishes off by 100 miles or 150 miles, which is approximately 300-ish kilometers. So let's say 300 kilometers. So 300 kilometers up, the satellite is put into orbit. You can put it at 400, you can put it at 500, you can put it at 1,000, you can put it anywhere you want. But you should put the appropriate speed for that, that's it. So let's say you're going to put a satellite, let me increase the height anyway. So, all right, 300 is fine. 300 kilometers, 300 kilometers. And if you want the satellite to be in orbit, work through the same thing. And this time I'm going to keep the G and M the same way. If you want, you can leave it as it is, or you can just plug it in, anything you want. All right, let's see. GR squared over, now the bottom is not going to be, let me do it all over again. Even at that height, this equation is always true. So for any orbital motion, that equation is always true. The only thing is the equation changes its format. Instead of R, it's going to be R plus H. So it's going to be R plus H squared. And what about the other one? MV squared over R or R plus H? What kind of a circle radius is going through? That's R plus H. So that's also R plus H. And one of these cancels off. One of the R plus H's cancel off. And you know that, M's cancel off too. And you know capital G and capital M can be substituted with small g and small r squared. You can do that. So we have ultimately this equation, R plus H What is V? V is going to be square root of GR square over R plus H. Work it out. 9.8 times 6.4 10 power 6 squared over R plus H. R is 6.4 10 power. R is 6,400 kilometers, and I said 300 more kilometers. So what's the total? 6,700 kilometers. So your total here is going to be 6.7 times 10 power 6. No squaring. So tell me how fast. Should be pretty close to the previous answer. You got 7.9 something. It should be very, very close to that. Tell me what answer. So 7.7 kilometers per second. You get around 7,700 meters per second, which is 7.7 kilometers per second. So the speed of that satellite should be around there. Oh, let me put the actual number. What is that again? 7740. 7,740 meters per second. That is the speed with which the satellite is supposed to be launched or put into orbit in order for them to stay there. So how do they do it? How do they do it? The rockets go up, and you can see that rockets don't just go up straight there. The rocket actually will start off like that, and then it starts turning. You've seen it turn, right? Yeah, it starts turning very soon. And then after that, the rocket is going to be basically flying. It'll take off, and it'll fly round and round, fly round and round, and keep rising higher and higher, and come to the right orbit. Once it comes to that, exact place, once it comes to that exact orbit, the exact height, the exact speed, then it detaches the satellite, leaves it there, and then returns. So basically, it's like you're just going there and then detaching it and say, all right, bye, I'm coming back. And then you come down. So that is basically how it is put into orbit, and they make sure that, yes, that is the right speed for it to keep going. And it won't lose its energy after that. There's nothing to stop it. Okay, so there's no fueling required, nothing. Now, for its operation, of the amplifiers and all the signal processing stuff and all those things, they need power. And for that power, they have solar panels. Get it? Any questions here? That's the speed. Now, if it is going at that speed, how long will it take to go and to complete one circular path? How long? How much time? You can figure the time out now. So what's the total distance from here all the way till here? What's the total distance? 2 pi r. Yeah, go ahead. So 2 pi r is the total distance. So distance is equal to speed times time. Simple equation. The distance traveled is the speed times time. So how long it's going to take? The time is going to be distance over speed. So distance is 2 pi r, and the speed is right there. So calculate 2 times pi times 6.4, no, 6.7. 6.7 times 10 to the power of 6 divided by 7740. Tell me how many seconds it takes.
5,430.
5,430 seconds. Roughly right. And which is how many hours? 1 point. Convert it to hours. Divide by 3,000. 1 point? Exactly.
Like 5.1.
Okay. So 1.51 hours, which is how many minutes? 90 something minutes. 90 minutes. It's back again. So it goes around the earth and comes back again in 90 minutes. And it'll keep doing that again and again and again. So how do you tackle any problem based on orbital motion? Start from here and go. Okay? So the time, so when satellites are put over there now, there are multiple kind of different kind of satellites. These are the kind of satellites that they go once in 90 minutes approximately. So every 90 minutes is coming back and scanning it. So there are some satellites which are actually spy satellites. Their main job is to kind of find out activities that are taking place on the ground. They take pictures as they keep going, and they find out the changes that are taking place in the pictures every 90 minutes. And it's not one satellite doing it, there are multiple satellites doing it, so they kind of have a continuously changing picture. You know, their pictures updated depends on satellites. How many satellites are spinning around, how many are actually helping us get this idea. So there are satellites that are looking at Syria and finding out if there's any unexpected activity going on. Are there kind of truckloads suddenly moving on the roads, going somewhere? And then, of course, they will send some ground people to investigate what's going on. And if they know that that is an illegal sort of thing, or that is something to do with arms and some stuff, then send something and bomb them. So spy satellites, there are many spy satellites doing its job. We don't realize it. It's just flying above us every 90 minutes. It's a small thing, and but it is able to do these things. It takes pictures. And there are weather satellites. The weather satellites do pretty much the same thing, but their job is not to spy on people, but spy on the weather, on the clouds and on the thunderstorms and all that stuff. So it takes pictures and sends it down. And when you look at all those pictures, and you can see which way it is moving and how fast they're moving too. So that's how they predict the weather. They see that, okay, right now it is somewhere around St. Louis, but that's where it is moving, and so it may reach Kentucky after this much time, according to that track. But nature is sort of weird, like we calculate, we do things, but suddenly, the nature will kind of shift its direction off, even beyond our calculations sometimes. And that's why something that is expected to reach here shifts off a little bit and it hits somewhere else. So that is possible, yeah, but all these images are taken by these satellites. And there are so many of them doing it all over the earth. And they take very clear pictures. The resolution is pretty high too. So they get pictures updated every now and then. So the weather satellites are doing its job all over the earth. And that's how you can actually get the weather of every place. In fact, your Google Earth, the clouds and things like that are updated. They're updated. Have you tried the weather on the Google Earth? Check on the weather icon. Check on the weather, and when you check on the weather, it'll show you the clouds. It'll show you the clouds, and if you zoom in to Louisville, and if it's snowing outside, you can see the snow falling there on the picture, on the screen. And if it's raining, you can see the rain. That's pretty good. So in fact, I sometimes go to Google Earth and look for any patterns that are moving our way, and I make my own kind of predictions according to what's happening there. So you can actually see literally the cloud moving from place to place. And it's a nice app to have, Google Earth. All right, so I'm trying to say, all right, so the spy satellites, weather satellites, they're all pretty close. They're all not too far away. They're all very close, and they're going around 90 minutes everything. Now, there are some satellites which are called parked satellites. Parked. It's like you're parking your car. Where's my car? My car is right there. Is it going to be there always? No? I mean, is it till I go get it? Is it going to be there?
Yeah.
So whenever I think of my car, I just look there and the car is there. Why is my car over there? Because it's parked over there. Is my car moving? It's moving faster than the speed of sound. And so am I also moving. So are you. We are all moving because the earth is spinning. So we are all moving at speeds more than speed of sound. My car is also moving, but my car is always there. How come? Because we are moving synchronously, and those are called geosynchronous orbits. Geosynchronous, which means what? They are far away. They're far away. Those are spinning at a speed which is exactly the same speed as the Earth's spin. You understand? How long does the Earth take to go around once? 24 hours. So as the Earth spins, that also spins like that together. They both go synchronous, which means whenever you want to look at the satellite, there it is. There it is. It's always there. And that's why your dish antenna, your dish, is it like searching for satellites every time? No, it's fixed. Where is it looking at? The satellite. So if the satellite is there and you're here, the dish is facing that way. You understand why the dish is facing in different directions? They're looking at different satellites. Now if I want to look at some satellite, some other satellite, not that, then I can face it that way, some other satellite. You can actually focus onto some satellites and pick up their signals. Now, what is the condition for that? Same thing. GMM over R plus H squared. That stays the same. On this side, M R plus H omega squared. See, I'm bringing in omega now. Because now we are talking about the Earth's spin. 24 hours is the time period. And you know omega is 2 pi over capital T. Get it?